Hello there. In this lesson, we're going to learn about reaction rate law. And reaction rate law is not so much a law as it is an equation, a relationship between concentration of reactants and how fast a reaction goes, right? So this is one you might do in your class. If you take some 3% hydrogen peroxide and you add your catalyst, you might get a nice slow bubbly foam that's created. But if you take 35% hydrogen peroxide, which is a little harder to find, you add that same catalyst and then away she goes a lot faster. So there's a relationship, a mathematical relationship between the concentration of reactants and the rate at which the reaction goes. And so that's what we're going to look at today. So the rate law is an equation that's related to the concentration of reactants. So in my example here, we have X and Y. These are reactants. And the A and B, these are coefficients. So what they find is that the rate is proportional to the concentration of the reactants raised to some exponent power. Now you notice that the exponents are m and n, not a and b. So the exponents aren't necessarily going to be the same as the coefficients. So you have to work that out mathematically. This proportionality is what you would see when you plotted these things. If you plotted the rate versus the concentration at a given point, you would see that you get a nice straight line. In order to change that into an equation, you have to add a constant. And so this expression here is what's known as the rate law. It's the proportionality, but turned into an equation by adding a constant. Okay. All right, in order to find the exponents and the constant from the rate law, so rate equals some constant times the concentration of the reactants to some exponent. So in this case, we got reactants, nitrogen monoxide here and hydrogen, and they're going to have exponents. Often we use m and n. I'm not sure why. That's supposed to be an n. And so what you have to do is you have to do experiments. So experiment number 1 here, we have starting concentrations for each of the reactants and then a rate at that time. And then experiment number 2, we do different concentrations. We changed the concentration of the first one there. We left this one the same, and we got a different rate of reaction. So you can use these different experiments in order to work out what this relationship is, what the exponents are, and what the constant is. And I'm going to show you that next. Okay, the first step we're going to go through here is determining the exponents of the rate law. Remember that the rate law, R equals some constant. In this case, it's the concentration of nitrogen monoxide and hydrogen. So nitrogen monoxide concentration to some exponent and hydrogen to some exponent. So the way to solve this is with different experiments. So you see 3 different experiments were done here with different concentrations of reactants and then different rates for those concentrations. So to find out what the exponent is, I find it easiest to just divide 2 of the experiments in order to come up with the exponents. I'll show you how in a second. I'm going to take experiment number 2 and divide by 1 because I see that the concentration of nitrogen monoxide here is greater in number 2 than it is in number 1. So if I divide those, I'm going to get a whole number, whereas if I went the other way, I'd get a fraction. So we're going to take experiment 2 and divide by experiment 1. We'll take the rate, which is, I guess I won't rewrite it there, or I'll run out of space. So I'm going to put the rate here, which is 5 times 10 to the negative 5. And that equals a constant, the concentration of nitrogen monoxide, 0.01 mole per liter, to that exponent, and hydrogen is 0.002 moles per liter, and that's to another exponent. Then I'm going to divide that by experiment number 1. So experiment number 1 is 1.25 times 10 to the negative 5 equals that same constant. Concentration in this one is 0.005 moles per liter. Same exponent, 0.002 moles per liter to the same exponent. So once you do this, ignoring my scratch from the beginning here, you'll see that some of these items can be canceled out because they're the same, and anything divided by itself, of course, is 1. So constant divided by constant, that equals 1. 0.002 to the power of n will divide by 0.002 to the power of n, and that'll equal 1. So we're just left with these two parts. So 5 times 10 to the negative 5 divided by 1.25 times 10 to the negative 5. Do that on your calculator, you'll end up with 4. And that equals 0.01 divided by 0.05, which is 2, to the power of m. So once you have it simplified to that, it's pretty easy. M has to be 2, right? 2 to the power of 2 is 4. So therefore, m equals 2. Awesome. So now we got one of these parts. We know that m is 2. So now we got to work at this next one here, the n part. So we'll go back to our experiments here, and I see that experiment 3 and experiment 2 have different values for hydrogen, but the same value for nitrogen monoxide. And so if I use those two, I should be able to do the same trick and work out what the exponent is on the hydrogen. So we'll do experiment 3 this time divided by experiment 2. So for 3, it's 1 times 10 to the negative 4 moles per liter per second equals the constant times, what are we here? Yeah, 0.01 mole per liter to the m. And then we got, actually we know m, we could put it in if we want, right? Then we know it's a 2. And then we got the concentration of hydrogen, which is 0.004 moles per liter, and that's to the power of n. I'm going to divide that one by the other one, which is 5 times 10 to the negative 5, and that equals the same constant, and it's 0.01 moles per liter to the power of 2, and we've got 0.002 this time to the power of n. Now we go back through and we see the parts that are the same. The constant is the same. The concentration of nitrogen monoxide is the same, so we can ignore all that. And now we need to do a little bit of division. So 1 times 10 to the negative 4 divided by 5 times 10 to the negative 5, that is 2. And then if you take 0.004 divided by 0.002, that is also 2 to the power of n. So in this case, n has to equal 1. So 2 to the power of 1 is 2. So there we go. Now we got both of the exponents. M is 2, n is 1. Okay, so we're coming right along here. Our rate law equation is filling in here. We have the exponents for nitrogen monoxide. We know the exponent on the hydrogen as well. So the next thing is to work out the rate constant for this set of conditions. So all you need to do then is rearrange your equation so that the constant is isolated. So that's what's down here, right? And then you just sub in values from any one of these experiments. They'll all have the same constant, which means any of those set of values will work. Let's use number 2, just randomly, it doesn't matter. So the rate here is 5 times 10 to the negative 5 moles per liter per second. And under that, we're going to put the concentration of nitrogen monoxide, which is this guy. So 0.01 moles per liter, that's to the power of 2. And the hydrogen is this guy, 0.002 moles per liter, and that's the power of 1. And so let's see what that all comes out to. So 5 times 10 to the negative 5 divided by bracket 0.01, where's the squared, times 0.002 to the power of 1, close bracket, equals. So I get 250. So 250 what? Well, we can work out the units here by looking at what we have in the equation. So we got moles per liter here, and then we divide by moles per liter squared and moles per liter. So that's really moles per liter cubed. So we're going to end up with moles per liter to the -2, right? This guy is a 1, and it cancels out one of these other guys. And then seconds is also on the denominator because it's per second, so it's going to be seconds to the -1. The other way to show that would be like 1 over moles per liter squared seconds. But generally they use these little exponents with the negative sign in order to show that. Now the little trick here is to take the sum of the exponents to work out what the reaction unit or constant unit would be. So seconds to the -1, that's always the same. Moles per liter, it's 1 minus the sum of the exponents. The exponents here is 2 plus 1 equals 3. So 1 minus 3 is going to be -2, which is what I ended up with over here by using the little math deduction. Okay, another way that rate law can be used is to determine some patterns between reactions and put them into groups. So zero order reaction means there's no relationship between the concentration and how fast a reaction will go. A first order reaction rate means there's a nice direct relationship between the concentration and the rate. And then if you go up from there, you start to get a curve as its exponential relationship. So the order can be determined from those experiments and the exponents that you end up calculating. So you would say that this is a second order with respect to the nitrogen monoxide, and this would be first order with respect to the hydrogen, and then overall it's a third order reaction because both of those factors will play a part. The only order reaction that we're going to look a little more closely at is that of a first order reaction. So first order reactions are where there's the reaction is governed by just one component, and that component has an exponent of 1 in the rate law. So the neat thing is that all those reactions follow what's called a half-life pattern, where the amount of time for half of a reactant to get used up or consumed is a constant. So if we started with 1 mole per liter here, the amount of time to get to 0.5 would be the same as the amount of time it takes to go from 0.5 down to 0.25. And that'd be the same as the amount of time to go from 0.25 down to 0.125, right? So all of these values here, these would always be a half-life. Decay of radioactive isotopes follows a half-life pattern, and it's what's used to express how long it takes, or what's used to calculate the time that a particle has been around based on the amounts of, mother and daughter particles from nuclear decay. First order reactions have a nice relationship between the rate law constant and that half-life, which is something that you can measure. All you need to do is take the ln of 2. Ln is one of those logarithms that has a base other than 10. And so what you do is you take the ln of 2. It's an easy thing that you can get on your calculator. 2 ln, it's always the same. So ln 2 always is 0.693. And that doesn't have any units. So if you want to determine the constant from the half-life or vice versa, you can do that with this little relationship here. So it says, what's the half-life of a reaction with the constant of 450 seconds to the -1? So the half-life would then be 0.693 divided by 450 seconds to the -1. And you would end up with divided by 450 equals. And I got 0.00154 seconds. So that's a really fast half-life. Let's break down really quickly. And it says, what is the rate constant for a reaction with a half-life of 4,500 years? Ooh. Okay, so in this case, we're trying to find the rate constant, so that's this part. And so to rearrange things here, we're going to take, the constant will equal, and be ln 2 divided by that half-life. And so what we can do is take our 0.693 divided by the 4,500 years, and you would end up with a constant of 0.693 divided by 4,500 500 equals, and I got 0.123154 again. Oh, right, of course, because 45 and 450 are similar numbers. So this time it's years to the -1 because we used a different measure of time, but you can see how you can easily convert back and forth there. Finally, all of that rate law stuff has just been related to the concentration of your reactants. And obviously we know that there's other factors that go into how fast a reaction goes, notably temperature. And so all those constants will only be good at a set temperature. And if you change the temperature, then that's going to change the constant, speeding up or slowing down the reaction, depending on whether you raise or lower the temperature. So there's this neat equation called the Arrhenius equation that relates the rate constant to other factors. And so you can see temperature is in there, and so is the gas constant and activation energy and a bunch of other stuff in here that we're not going to bother with. But I just wanted you to know that there was a relationship between the constant and the temperature, and it can be worked out. If you like chemistry and you followed along, I'm sure you'll get to use this at some point, just not in grade 12, not this year.